Okay, so in this video I'm going to have a look at the Leaving Certificate Higher Level Paper 2 for 2018, and I'm going to have a look at question 8. So we have Acme Confectionery makes cakes and chocolate bars. They've launched a new bar called Chocolate Crunch. The weight of these new bars are normally distributed with a mean of 4.64, so I'm just going to write this down as I go along. The mean is going to be 4.64 grams, that's the population mean, and the standard deviation is 0.12 grams. A sample of 10 bars, so our n is equal to 10, is selected at random and the mean weight of the sample is found. Find the probability that this mean weight of the sample is somewhere between 4.6 grams and 4.7 grams. So the question we're actually asked here is to find the probability that X bar is between 4.6 grams and 4.7 grams. So this is the question we're asked to find here. Okay, so what we got to do now is first of all just convert these X bar values to Z values, and then look up the probabilities. So let's take 4.6 first. So we've got to work out the Z value for 4.6. So your formula for, because this is a sample we're taking, your formula for Z is just going to be your X bar, your mean, minus your population mean, divided by the standard error of the mean, which is sigma over root n. So we have an X bar here, or this value here, if you like, of 4.6, this is our X bar, if you like, minus our mean, which is 4.64. We've got to divide this by the standard deviation, or sorry, the standard error of the mean, which is our standard deviation, which is 0.12, divided by the square root of the sample size, which is square root of 10. Now when you work this out, you'll get minus 1.054, minus 1.05. We'll do it to 2 decimal places. That's the first one. Let's work out the second one then. We've got Z is equal to 4.7, so we've got to subtract 4.64, divide by the standard error again, which is 0.12, divided by the square root of 10. When you do this, you get 1.581, so let's say 1.6. Okay, so let's have a look at, well actually we'll do that to, we'll say 1.58 there actually, we'll do to 2 decimal places again, 1.58, do to 2 decimal places in each case. Okay, so let's just change our question around here. This was the question we were asked, so let's just change that around now to reflect the Z values. So we want our Z values now to be between minus 1.5 standard deviations, 1.05 I should say, and less than 1.58. Now these values we can look up, or we can work out. So let's just change this around. Let's see exactly how to work this out. Now we're going to, if you actually draw this, it'll look something like this. So we'll have 0 here, we'll have minus 1.05, and we'll have 1.58 up here somewhere. It's not quite to scale, but anyway. So we want to find the probability of being in here somewhere. Now how do we do that? Well, we're going to find the probability of being less than 1.58. So in other words, we're going to find the probability of being down here, this entire area, minus the probability of being down here, and then we're going to subtract them. So we're going to work this out, probability of being less than 1.58 standard deviations above the mean, minus the probability of being less than minus 1.05 standard deviations above the mean, and that will give us our area in the middle. So let's just write that out. So this is going to be equal to the probability of z being less than 1.58. So that's this red area, all this red area, all this area down here, minus the probability of z being less than minus 1.05. Now this here we can work out, we can just use our tables to work this out. We have a less than and we have a positive value here. So we'll just write that out again. So this is going to be equal to the probability that z is less than 1.58 minus, now this here we've got less than, which is fine, but we have a negative z value here. We can't look up negative z values in our tables, so you got to make this positive somehow. So again, if you were to draw this, it would look something like this. We have our minus 1.05 down here, and we have 0 here. So we want to find the area, this area down here. Now we can't do that by looking up minus numbers. We can only look up plus numbers in our positive numbers in our tables. So we have a 1.05 here, which is positive, and this area here is the same as the area down here. So if we can find the probability of being greater than 1.05, then that will work. Now again, our tables will only give us the probability of being less than a particular z value, so being less than 1.05 will be all this area down here. So if we look up 1.05 in our tables, it'll give us the probability of being down here. 1 minus that will give us the probability of being up here, which is the area we want. So what we're going to do is 1 minus the probability, so all this here is just equal to 1 minus the probability that z is less than plus 1.05. So these are the values we can actually work out from our tables. Now this here, when you look it up, is just 0.9429. We've got minus 1, and then we've got minus minus, which is plus. This here we can look up, and that's 0.8531, 0.8531. Now when you do all of this, I'll just move it over here a little bit, we get 0.796. So the question was, find the probability that the mean weight of the sample is between 4.6 and 4.7. Well, this is our answer here. So this is it here. This is our answer. Okay, so that's it really for part 1 of A. So let's have a look at part 2. So a company is surveying 400 people. They've surveyed 400 people, chosen from the population of people who had bought at least one chocolate crunch bar. Of those surveyed, 324 of them said they liked the new bar. So 324 out of 400 said they liked it. Create a 95% confidence interval for the population proportion. So this word here is very important, population proportion, who liked the new bar. Give your answer correct to 2 decimal places. So we've got to work out a confidence interval for the proportion. Now, in order to do that, we need our p hat here, our sample proportion. Our sample proportion was 324 people liked it out of 400. And remember as well, just read the question carefully. They're looking for the population proportion who liked the new bar, So the number of people who liked it was 324. Now that is just 0.81. So that's our p hat. So in other words, our population proportion is going to be greater than and less than a particular value. That's going to be our 95% confidence interval. So what is that value? That value is going to be our p hat plus and minus our margin of error. And our margin of error is going to be worked out by multiplying 1.96 by the square root of p hat times 1 minus p hat divided by n. That square root there includes the n as well, by the way. Okay, so we got to just work this out. Now, this is going to be 1.96 times the square root of 0.81 times 1 minus 0.81 all over n, which is our sample size, which was 400. Now, so we're going to work out P, the population proportion. Create a 95% confidence interval for the population proportion. So this is P here. So that's going to be greater than or less than, greater than or equal to, less than or equal to our P hat, our sample proportion, which is 0.81 minus this margin of error here, minus 1.96 times the square root 0.81, 1 minus 0.81 divided by 400. And on this side then we'll have our 0.81 plus our margin of error 1.96 times the square root 0.81, 1 minus 0.81 divided by 400. So you just got to work those out. It's really just a lot of calculator work, and you finally end up with your margin, or your 95% confidence interval for the population proportion who liked the new bar. Give your answer correct at 2 decimal places. So when you do all of this, you can do this on your calculator. Do it in steps again. Don't try and stick it all into your calculator at once. And you end up on the left hand side with 0.77. And on this side you'll end up with 0.85 when you work all this out. So somewhere between 77% and 85% is our population proportion, people who actually liked the new bar. Okay, so that's that question. Now let's have a look at part B, part 1 of part B. So put 1 tick in the table for each statement to indicate whether the statement is always true, sometimes true, or never true. In the table, N stands for the sample size, and P hat is the sample proportion. Okay, so first one. Now we have when forming confidence intervals for fixed N and P, an increasing confidence level implies a wider interval, and that's going to be always true, because when you increase your confidence level, so we've just done one for 95%, we've done 95% confidence level. If you increase that to 99%, so you're 99% sure, if you like, that the true population is between your particular limits, then your limits will be wider because you're more confident that the population proportion is between these particular limits. So in order to be more confident, your limits, or your confidence interval, will be wider. Now the second one, as the level of P hat increases for fixed N, the estimated standard error for the population proportion increases. Now the standard error for the population proportion is given by this here. It's in the tables, but it's just given by square root P hat 1 minus P hat divided by N. Now we've used this in the previous part of the question. So this is the standard error, or the standard deviation. Now what they're saying here is, as the value for P hat increases, so as this value here increases, the entire thing, the entire standard deviation, the entire standard error increases as well. Well, that's going to be sometimes true. I'll just explain why. This numerator here, this part here, P hat times 1 minus P hat here, that's actually a quadratic expression. It's P hat minus P hat squared. Now it's a negative quadratic, which means it goes up and it goes down. So it has a maximum value, so it increases and it decreases. as p hat changes, the curve here will increase and then decrease. So as p hat increases, you'll find yourself coming up here, then it will maximize, and we'll see that actually in the next part of the question, where it maximizes, and then it will eventually decrease. So this fraction then, as a result, because the numerator increases, the fraction will increase. When the numerator is decreasing, when the top part of this fraction is decreasing, this fraction will decrease. So hence the entire standard deviation, the entire standard error, will increase and decrease as p hat increases and decreases. So sometimes it increases, sometimes it decreases. Okay, what about 3 here then? As the value of p hat times p1 minus p hat increases for fixed n, the estimated standard error of the population proportion increases. Now again, this is going to be always true. So as the value of this entire expression here, which is the numerator of this fraction, the top part of this fraction, as that increases, the estimated standard error for the population proportion will increase. So in other words, as the numerator of fractions increase, the fraction itself will increase. So for example, if you've got 1 over, sorry, let me change that. If you've got 1 over 5, 2 over 5, 3 over 5, 4 over 5, 5 over 5, and so on, you can see the numerator here is increasing. What's happening to the entire fraction? We have 1/5, 2/5, 3/5, 4/5. The entire fraction is increasing. So as p hat 1 minus p hat increases, the entire fraction here will increase, therefore the entire standard error will increase as well. So that's always true. Now what about the last one here? As n, the number of people sampled increases for fixed p hat, the estimated standard error of the population proportion increases. Well, that's never true, because as n, the number of people sampled increases, so as the denominator increases, what happens to the fraction? This is for fixed, the top part will be fixed, but the n will increase. What happens to the fraction? Well, the fraction decreases. So to give you an example of that, if you have, I don't know, 4 over, no, we'll do an easier one. Let's say 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6. So here the denominator is increasing. So you're going from a half to 1/6 here. The denominator is increasing. What's happening to the entire fractions? The entire fraction is decreasing in value. So it doesn't increase, it decreases. So as n increases, this entire fraction here will decrease, therefore the entire standard error here will always decrease, not increase. So that's part B, part 1 of part B. Okay, let's move on to the next part, and this is, we've done a little bit of this previously, but use calculus or otherwise find a maximum value of this thing here. So we have p hat times 1 minus p hat here. So this is a function. You can use x's here, you can use y's, but it's basically a quadratic expression. So let's let it equal to, let's say, y, and it says use calculus or otherwise. Usually go with what they suggest, but there's probably other ways of doing this. Maybe you could draw it or something like that, but you can do it using calculus. Let's find dy dx, or it's actually dy d p hat here rather than x, but anyway, we want to differentiate this. Well, if you look at p hat 1 minus p hat, we did this earlier, that's just equal to p hat minus p hat squared. So what happens when you differentiate that? Well, differentiate this, you'll just get 1. Differentiate minus 2 p hat, that's going to be minus 2 p hat to the power of 1. So this is what you get when you differentiate it. We have to find the maximum value of this. We know that this thing here is it's a negative quadratic, so it has a maximum here, maximum value here somewhere. So how do you find this maximum value? Well, the slope is going to be 0. The slope of the tangent is going to be 0. This is the slope of our tangents here. So in other words, 1 minus 2 p hat, let our slope equal to 0 and see what happens. Well, you get minus 2 p hat is equal to minus 1. that gives you p hat here equal to minus 1 over minus 2, or just 1 over 2. P hat will be equal to a half. In other words, the x value here, or the p hat value on our x-axis here somewhere, will just be a half. So this expression here is maximized when p hat is equal to a half, or our standard error for the population proportion will be maximized when p hat is equal to a half. So that's it. I think that's all we were asked to do. Use calculus or otherwise find the maximum value of p hat minus p hat here. Okay, well actually we haven't quite gotten there so far. It's maximized when p hat is equal to a half. So what happens when we were asked to find the maximum value of this expression here? So in other words, when p hat is equal to a half, that gives you p hat 1 minus p hat is going to be equal to a half times 1 minus a half. So we've got to maximize this expression here by putting half into it. When you do that, you'll get half. Half times 1 is a half, minus half times half is a quarter. Not a half here, a quarter. So half minus a quarter is 1/4. So this is our answer here. A quarter. So that expression then is, this expression here is maximized when p hat is equal to a half. What is the maximum value? The maximum value is a quarter. Okay, now you can check that as well, by the way, by doing a second differential here. So let's see, where's our differential? It's here. This was our differential here. This is our first differential here. If you did a second differential, let me do it here because I know I'm going to run out of room later on. Obviously don't do this in an exam, do it underneath here somewhere. But if you worked out d2y d p hat squared, so do a second differential. So if you differentiate 1, you'll get 0. Differentiate this, you'll get minus 2, which is less than 0. It's negative, which implies we have a maximum value. It's a maximum value. Maximum value here. So it's maximized at p hat equal to a half. Maximized. Okay, so that's it for part 2. Let's have a look at part 3. It says find the largest possible value for the radius of the 95% confidence interval for a population proportion given a random sample size of 800. So we've got to maximize our margin of error. So in other words, to maximize our margin of error here, our margin of error is given by 1.96 square root p hat 1 minus p hat divided by n. Now in our particular case we want to maximize this, find the largest possible value for this margin of error here. So in our particular case it's going to be 1.96 times the square root of, now we want the largest possible value for our standard error, so we know that that's maximized at a half when p hat is a half. So 1 minus half here, 1 minus a half divided by, now our sample size now is 800. When you work this out you will get 0.034648 and so on, 228. So that's it. I mean, find the largest possible value for the radius of our 95% confidence interval. So whatever our p hat is, whatever our sample portion is, we're going to add and subtract this here. So this will give us our actual radius. So this is our answer here. Okay. Now, so let's do part C, which I think is the last part. This is a financial maths question, and the confectionery has an employee pension plan. For an employee who qualifies for the full pension, Acme Confectionery will pay a sum of 20,000 euros on the day of retirement. It will then pay a sum on the same date each subsequent year for the next 25 years. So at a particular date, they will, on the date of retirement, they'll get 20,000 euros. Then they'll get 20,000 euros the following year, and the following year, and the following year. However, each year the employee is paid the particular sum that is 1% more than the amount paid the previous year. So it's going to increase by 1% every year. What is the sum of money the company have set aside on the day of retirement in order to fund this particular pension? And there's also going to be an annual interest rate, an AER of 2.4%. Okay, so let's just see what's happening here. We need to let's just do a little timeline here and see what exactly we're dealing with. So let's take let's do this in white, I think. Yeah. So let's take this as being T0 is now, T1 is a year's time, and so on, and then we're going to go up to year 24, and let's do year, this is T24 and this is T25. Now what's going to happen here is that we're going to have 20,000 euros now. So we're going to get 20,000 euros now. So let me just put that in here. On the date of retirement, 20,000 euros. Okay, so what's going to happen in a year's time is we need to find the present value of this amount here. That's going to be 20,000 euros, 20,000 euros multiplied by 1.01, because you've got to increase this by 1%. So you've got to get multiplied by 1.01. 1.01. So that's increasing this 20,000 by 1%. However, there's also from the question here a 2.4% AER. So 20,000 euros will have increased in value by 2.4%. So we've got to bring it back to present value. So we've got to all of this amount here we've got to divide by 1.024. In other words, I'll show you that in a second. 1.024. In other words, what we're really doing here is we're looking at, if you take your basic formula, final value is equal to your present value 1 plus I to the power of t. So the present value then, the present value here is going to be the final value, which is this amount here on top, divided by 1 plus I. Our I in this case is 2.4% or 0.024 as a decimal to the power of t. So this is what we're actually doing with our 20,000 euros. So our final values are actually 20,000 euros increased by 1%. So this is our top line here. This is how much we're going to be paid, or she's going to be paid in a year's time. So what's the present value of this amount here? Well, you divide by 1 plus I, which is 1 plus 0.024 to the power of t. Well, it's only 1 year, so we just put in 1 year here. Okay, so you can do that again here, and it would be, let me just actually do another one. Let's do one more here. Let's put in another timeline here. Let's put in year 2. Let's do that a little bit straighter. Okay, so we have T2 here. So let's take this amount here. So how much will she be paid at this particular stage? Well, there's 20,000 euros will have been increased here by 1% by multiplying by 1.01, but you've got to increase again by 1.01, so it's 1.01 squared. And what's the present value of that amount then? Well, it's going to be 1.024. This time we're talking about 2 years, so that's got to be squared. And so on. You've got to keep doing that for 25 years. Now let's have a look at, we'll have a look at 24 and 25. So just get rid of these. Let's have a look at 24. So again, we'll just take 24 here, bring it back to the present value again. So what have we got? We've got 20,000 anyway, 20,000 euros. How much has that increased by at this stage? Well, each year it's increased by whatever this number here is, this timeline here. So this is 1.01 to the power of 1. This is 1.01 to the power of 2. So this must be 1.01 to the power of 24 at this stage. All divided by, again, it's 1.024. This time it's the power of 24. And finally then we'll just do the last one and then we'll put it all together. So we have 20,000 euros here, and this is going to come back, and we'll just end up here with 20,000 euros again, 1.01 to the power of 25, all divided by 1.024 to the power of 25. So these are all of our present values. These are all of our present values, and a few dots in between these two here. Okay, so let's see if we got everything. Then paid a sum, same date, each subsequent year for the next 25 years. So each year the employee is paid a sum which is 1% more. So we have our 1% included here, and we have our 2.4% included on the bottom here. So we've got to put all these, we've got to add all these up. When we add all these up, this is the amount, the actual amount that the company must have in the fund in order to pay the employee this amount, 20,000 euros plus 1% every year. Okay, so let's put them all together in a row then. So we have 20,000 euros. So the amount required, we'll call it amount required, let's say, is 20,000 euros first of all, plus 20,000 times 1.01 divided by 1.024 to the power of 1 plus 20,000 1.01 to the power of 2 divided by 1.024 squared plus, and so on. I'm just going to put in the last one here, 20,000 1.01 to the power of 25 divided by 1.024 to the power of 25. So this is actually a geometric series. So what we're going to do is use that fact to add all these up, and that should give us our amount. So first thing I'm actually going to do, a couple of ways of doing this. You can leave it as it is, but what I like to do is factorize out the common factor here, which is 20,000. You don't have to, but it sometimes makes it a little bit easier. So I'm going to take this 20,000 and just take it out. And so what I actually end up with is 1 plus 1.01 over 1.024 plus 1.01 squared divided by 1.024 squared plus all the way up to 20,000. Oh no, I've left that out. I should take that out altogether. 1.01 power of 25 divided by 1.024. Now I just have to do a geometric series, some of the geometric series on this amount here in the brackets. Okay, so let's do that then. So we have 20,000 here. Within our brackets we have a sum of a geometric series. So let me just write down the formula for that. So in this particular case we have the sum of, we want to do sum of 25 years in fact, so it's going to be a times 1 minus r to the power of n over 1 minus r, where a in this case is 1, a is equal to 1. Or here is, we're just multiplying each term by this here actually, because you square the top, you're squaring the bottom, and so on. So you're multiplying by 1.01 over 1.024 in this particular case. And our n then in this particular case is, you have to be a little bit careful here, we actually have 26 terms, because if you look at this, this is the power of 1, this is the power of 2, so we have 25 terms from here up to here, but we have this extra term here which is 1, so in actual fact we have 26 terms in total. So let's work that out. Now we have 20,000, and in here we're going to have A, which is 1 times 1 minus or, which is 1.01 over 1.024 to the power of n, so this is all to the power of 26. That's that one there, and then divided by 1 minus or, which is 1.01 over 1.024. And this is the amount that needs to be in the account at the beginning of the 25 years. So I've done this. Now you can spend a few lines in between doing it. Again, I wouldn't try typing all this into your calculator. Just do little bits at a time. But I've worked out the top line here is 0.30087 17589. That's going to be divided by 0.013, 0.013, 6718, 75. Okay, now when you work this out, then you get 440132.40 euros. So this is your answer really. You need 440,132 euros and 40 cents in the account at the beginning of the 25 years. Let's just go back and make sure we have everything we need. What is the sum of money must the company? What sum of money must the company have set aside on the day of retirement in order to fund this pension? So that's it really. This is the amount to the nearest cent here. So this is our final answer here.